Okay, I decided to break the video up actually, so this is part 2. So for those people who are watching it on YouTube, an hour is pretty a long time to watch something. They're not going to watch it for more than an hour, probably not even that long. So we're going to break this up. This is part number 2 of the SQL lecture, continuation of the previous lecture. More SQL? Could there be more? There is more. So relations as bags, grouping and aggregation, and database modification. So let's see. We have the union, the intersect, and the difference. When we start looking at bags, we're starting to look at sets. So we're going to put stuff together in a bag, and then we're going to cross one bag with another bag, or one group with another group. So the union, the intercept, and the difference of the relation are expressed by the following forms. We have one subquery union another subquery, or one subquery intercept, or one subquery except. So this is where we're going to take a subquery. We're going to get more than one result that comes back, and we're going to union it, or we're going to intercept it, or we're going to do an except. So the union is everything together. The intercept is where they differ, or excuse me, where they have the commonalities. And then the except is one set minus the other set. So what do we have here? Here's an example. So from the relation likes, and likes has drinker and beer in it, and sells that has bar, beer, and price, and frequents that has drinker and bar. Find the drinkers and the beers such that the drinker likes the beer, well that would be a good thing, and the drinker frequents at least one bar that sells the beer. That's another good thing. So otherwise we wouldn't have any sales. Here's our solution for this troublesome problem here. We have select star from likes. So here's the format. We have one subquery with opening and closing brackets, which is going to give us the select from star from likes, everything from likes, and we're going to intercept that. We're going to see where it matches. Select drinker comma beer from sells comma frequents, where the frequents.bar is equal to sells.bar. So the people that frequent the bars along with the bars that sell, sells.bar that sells. So the drinker frequents a bar that sells the beer that they like. Those are the most profitable bars, I think, actually. But we're demonstrating here two subqueries that are connected together with an intercept. And now you can take the intercept and use any of the union, intercept, or except in the same context to get different results, depending upon what you're looking for in that query. So what do we mean by bag semantics? Although the select from where statement uses a bag semantic, because it's a grouping, the default for union, intercept, and difference is a set semantic. So we don't have more than one in the set. That is, duplicates are eliminated as the operation is applied. So a set is generally the set of A, B, and C. The bag is 2 A's, 1 B, 3 C's. It's all stuffed in a bag, not necessarily in a set format. So, the motivation here is efficiency. When you're doing a projection in a relation in relational algebra, it's easier to avoid eliminating duplicates. Just work one row at a time. Then when doing the intercept or the difference, it's most efficient to sort the relation first. So you're only working with one of each. At that point, you may also well eliminate the duplicates anyway. Because if you already have A, B, and C, what do we need 3 A's for? Is it one of the A's, or is it one of the B's, or one of the C's? So we just keep one of each. We turn it into a set. And if we do that, then the calculation itself is more efficient than working with a bag. Because why do we want to increase the search space? We don't have to. So controlling the duplicate and elimination, this is when the keyword distinct actually came from. So we can force the results to be a set instead of a bag by using the keyword distinct. So select distinct price or distinct name or something. It's only going to come back with one of each. So it eliminates duplicates. Forces the results to be a bag, i.e. don't eliminate the duplicates by using all, as in union all. So if you use the all, then you're forcing it to be a bag. If you use the distinct, you're forcing it to be a set. because you're going to create the set for you manually, or you're going to go union all. Give me all of it, don't remove anything. So here's an example of how to use the distinct. From sales, where we have bar, beer, and price, find all of the different prices charged for beers. So one of each of the different prices, select, and here's the keyword distinct. So select distinct price from sales. Okay. Notice that without distinct, each price would be listed as many times as the bar beer pairs existed. Is that going to eliminate any speed in the query? This query, no. It's just going to eliminate and reduce the size of the result space that comes back. But if I was using that result space in a subquery, then I'd have a smaller result space, smaller number of rows to actually have to go traverse through if I were doing this with a subquery. So the efficiency is really seen when you are combining subqueries together, unioning one subquery with another one. Then the distinct's really going to help you because it's going to eliminate all the duplicates for you. So it makes the search space smaller. You don't have to keep, oh, I got A. Oh, I already have A in there. A again, A again, A again. You don't have dozens of A's in there when you only need one. Is it in there or not in there? Here's an example of the opposite. If we do the all, uses the relation frequents here for drinker and bar, and likes drinker and beer. We're going to list the drinkers who frequent more bars than they like beers, and does so as many times as the difference of those counts. So we're going to use two subqueries, and we're going to do except all. Except all gives us a bag instead of a set. So select drinker from frequents, except all selects drinker from likes. So the drinker is not in the likes table. So list the drinkers who frequent more bars than they like beers. So they go to more bars than they like the beers there, and does so as many times as the difference of those counts. So it's going to go through all of them, all the different combinations. Lo and behold, the join expressions. So SQL provides a number of expression forms that act like varieties of different joins in the relational algebra, but uses bag semantics, not set semantics. So those expressions can be standalone queries or used in place of a relation in the from clause. So from, you can join two tables together, or from, or use the two tables on the from. So we have products and natural joins. So natural join is the obtained by R natural join S. So the right with the left, or left with the right. So you're going to join to, the product is obtained by the R cross join S. So if the product join would be, for example, if I have 5 rows in table A and 6 rows in table B, the product would be 5 times 6 actually in terms of the number of rows that I'm looking at versus the natural join. And if I have 5 rows natural join in table A and 6 rows natural join table B, it depends on whether or not I join A with B or B with A as to how many I'm going to have left over. So I can do an inner or an outer. The inner join takes only the matching, the outer join gets everybody else. So what I really want in reality, sometimes I might just want 6. That way I'm only going to get an empty space for the non-matching row in the first table. If I want to do an inner, then I'm going to get 5. I'm going to take the first one, match it with the second one, and only return where they match instead of a combination of all of them together. Knowing how to do the joins will help you solve problems in which you have students, let's say for example, that are at a university and you're not necessarily taking a class right now. So if you're not taking a class, then you're not going to have an entry in the registration table. If you don't have an entry in the registration table, you do an inner join on students with registrations, you're not going to show up in the system. If you do an outer join, you're going to show up, but you're going to be showing up with no classes associated with you. You're still in the system, you're still a student, but you're not taking any classes, so you don't have a registration entry. You're going to get more. The count's going to be higher one way than it is the other way. You're going to have a more inclusive or exclusive. But maybe you don't want. Maybe you just want currently enrolled, currently registered students. then you're only going to get the ones who are in the registration table if you go from A to B, and if A is shorter than B in terms of the number of rows. An example, likes natural join serves. So the relation can be represented in a parenthesized sub-expression as well. So let's take a look. Likes natural join serves. Our theta join, where we have drinkers join frequents on, name is equal to drinker. If we're going to do the join, as I mentioned earlier, we want to do this the most efficient way. We join on the keys, because then we have the index that takes care of a lot of the speed for us. On the theta join, we have the R join S on a condition. So is a theta join using the condition for the selection, where something is equal to something. Example here, using drinker's name and address and frequents drinker and bar. We can still do the join even though we're not joining keys. We can join any attribute we want on any other attribute that we want with any condition that we want. So it doesn't have to be an equals. It could be less than, greater than. Any type of combination that we want is going to give us anything that we want in terms of the join. Is very flexible. Gives us all D, A, D, B quadruplets, such that the drinker D lives at address A and frequents bar B, if we're going to do drinkers and join. The syntax for the query that you're going to run on the joins is going to be particular to the database that you're using. Oracle has different join expressions. Some of them actually use natural join. They use the words natural join. Some of them just use join. Some of you use outer join, inner join. Oracle uses pluses and minuses after the join with a theta expression. So you may or may not necessarily be able to know at this point the syntax, depending upon which database you're going to use this with. Joins are one thing that change between different syntaxes. You know, they say SQL is a standard, we're on SQL 2. But there are slight variations, and the joins is one of the areas of the variations that you run into. So, slight variations between database manufacturers because not everybody believes in the same kind of syntax. So the theta join, remembering it's on a condition where something is equal to something else, and then one table or the other table. And so it's giving us all of the intercepts. The outer join, R outer join S, is the core of the outer join expression. It's modified by the optional natural in front of outer. Optional on condition after the join. Optional left, right, or full outer join. So left is padding the dangling rows of the right of R only. Right is padding the dangling rows of S. Are you going to join left to right, right to left, whichever one's going to get padded. Because you're going to have dangling. If I went from A to B, and A had 5 and B has 6, I'm going to get 5 if I start with A and join to B. If I join B to A on the left, then I'm going to end up with 6. And I'm going to have padding on the 5th. Will I have padding on the right to the left if I do A to B? If I pad it by telling it to do natural outer, if I say optional natural, it'll naturally join only the matching ones. If I leave that out, go left to right, or go full outer, then I'm going to get both. Not to be concerned with the syntax for it. I'm going to show you the syntax for it. Probably not until the next interactive meeting, or maybe I'll show it to you later today. It depends on how late we go. The syntax, you really need to see it working in terms of sample queries, and I have some sample queries to show you in another lecture. But just keep in the back of your mind, there are many different options in joining, and it's generally going to be outer, inner, left to right, right to left, natural or not natural, in terms of what's going to happen with that. And then the theta join on the condition. Most of the joins that you're going to get are going to be on conditions, actually, for the most part. We also have aggregations that occur in the language. An aggregation is a sum, an average, a count, a minimum, a maximum of some nature. What does that mean? We can run a formula on the select. Select average, select a sum, select something. It can be applied towards the column in the select clause to produce the aggregation on the column. So also the count works the same way. So count asterisk, as an example, counts the number of rows. So do you want to count asterisk or do you want to count on a name of a row? Depends on whether or not you have null or not null in there. So the count's the funny thing. So on the aggregation, here's an example of how to use one on average. So from sales, where we have bar, beer, and price, find the average price for Bud. Okay, so we want to know what do people sell the average price for Bud for. Select AVG, average. Slight notation as well between different database manufacturers. Your formulas, your aggregations are going to be different depending upon the database manufacturer. Some of them have min, max, average spelt out. Some of them go AVG. The concept's the same. The syntax is slightly different. Varies a little bit between database manufacturers again. Same thing with the joins. Average is pretty, and some is pretty standardized though. Average price from sales where the Bud is equal to Bud, or the beer is equal to Bud. So I got the average price. Substitute average in for sum, for count. You can count the price. Well, what if a price is missing? And that's going to be different than the count with the asterisk in it. So, eliminating the duplicates in an aggregation. So you can use distinct with it, and use distinct inside of the aggregation. So distinct price. Count to the distinct price is going to give you different than count the price, because what if the price is the same for a couple of different beers? So distinct inside the aggregation causes the duplicates to be eliminated before the aggregation occurs. So you could count the number of different beers by using distinct with the manufacturer or with the name of the beer. But then on your name you're going to have problems if you have Bud Light with a capital B and Bud Light with a smaller b. That's two different beers. It's going to count two different names. So an example here might find the number of different prices charged for Bud. Select the count of distinct price, in this particular case, from sales where the beer is equal to Bud. Nulls are ignored in the aggregation. That's how your counts and your sums and everything else is going to get messed up. Null never contributes to a sum, an average, or a count. It can never be a minimum or a maximum of a column either, which means you can't do a minimum on a column and end up with an empty column. Not going to work. So if there are no non-null values in the column, the result of the aggregate is null. So it's going to come back with null if there's no non-nulls. So sometimes you actually see this in web forms when you have signed up for, I don't know, Barnes & Noble or something, or Amazon. You have an account, but you have never ordered anything. So it comes back to tell you your average something or other. It comes back and says null on it. You're like, why does it say null? It's because there's no non-null values that came out of that, and it counted the number of purchases you've made in the past, but you haven't made any purchases yet. You're a brand new customer. So if you make one, it comes back and says, hey, your previous purchase was this. Otherwise, the form says null on it. I'm like, wow, how weird. So, example of the effects of null, the number of bars that sell Bud. This is what I was trying to tell you before. So if we select the count, that's safer. That's the better query. The number of bars that sell Bud will count them, everything, from sales where the beer is equal to Bud. Well, what about selecting the count price, the number of bars that sell Bud at a known price? Well, if we don't have the price in there right, or there's a problem, or one of the prices was left out, it's not going to count it. So the count's going to be different, depending upon what we're going to count here. So, grouping. Not the first time that's happened in a class. All right, so we have grouping as well. So we can follow the select from where expression by group by. If we're going to have an aggregate out here, then we're probably going to group it by something. If we group it by something, then we can show that beer, Bud Light average price, Michelob average price, something average price. So you can follow, we also have a having as well, but group by or grouping. So you may follow a select from where expression by group by and lists of attributes that grow by the group. So the relation of the results from the select from where is grouped according to the values that are in the attribute. And any aggregation is applied only within each group. So here's an example of grouping. From sales, where we have bar, beer, and price, find the average price for each beer. So here's the trick. We have select beer that must be in the select clause, and then we have average price from sales, and then we have to put in this group by beer to know that we're going to group it by beer. Otherwise we don't know what we're going to group it by. If we put average, select beer, comma, something else, comma, average price, we can change it so we can group it by something else, or we can group it by beer if we want to. But this just tells us one beer after another beer with the average price. So here's another grouping from sales. We have bar, beer, and price, and frequents, drinker, and bar. Find for each drinker the average price of Bud at the bars they frequent. So select drinker, comma, average price from frequents, comma, sales, where the beer is equal to Bud and the frequents.bar is equal to sales.bar, group by drinker. So this one's pretty, this is okay. Compute the drinker bar price of Bud rows first, then the group by the drinker at the end. So the group by always goes at the end of the query. It can be followed by a having. It can be followed by any query in which we're going to do an aggregate, and we're going to aggregate it on a select clause, so select drinker. If we don't put this in here, we just get the average price. We get one number that comes back. If we put drinker in here, we get each one of the drinkers along with an average price that's associated with it, and then the aggregate is grouped by that particular drinker. Here's the restriction on the select within list that's with aggregations. So if any aggregation is used, then each element of the select list must be either part of the aggregation, part of the aggregate, or an attribute of the group by list. You actually have to include the group by and put in the name of the select attributes that you're putting in there. Otherwise the query will come back and give you an error message. The query won't run. It needs to know how to group it. So here's an illegal query example. What do we got here? We have, you might think you could find the bar that sells Bud the cheapest by doing this. Select bar, comma, minimum price from sales, where the beer is equal to Bud. But this query is illegal in SQL. Why? The bar is neither, what we're looking at is the problem is right here. Bar is neither the aggregate, it's not in here. So if it was minimum bar, so if we said select price, comma, minimum price, that would work. But why would we want that? I don't know. It's not part of the aggregate, nor it's on the group by list. So we fixed the problem by adding in the group by. So we put on the bottom group by bars, group by bar, and then we have it. So we have to actually do this to it. We have to put in a group by drinker. So this is the correct query, where if it's not a member of the aggregate, which it isn't, it has to be on the group by. If we don't group it, we get an error message. It's illegal. It doesn't know how to group it, actually, which is the problem. We also have, and you can't use a having instead, it has to be a group, so, which is funny. So we have a having clause. Having condition may follow a group by clause. You can have them both together. If so, the condition applies to each group and groups not satisfying the condition that are eliminated. So having something. Requirements of the having condition. The condition may refer to any relation or row variable in the from clause. So anything from the from clause. They may also refer to attributes of those relations, as long as the attributes make sense within the group. So it's either an aggregate grouping, a grouping attribute, or it's aggregated, one or the other. So let's see an example, because this doesn't make any sense until you see it. So to example the having from sales, and sales has bar, beer, and price. And we have beers, its name and manufacturer. Find the average price for those beers that are either served at least 3 bars or are manufactured by Pete's. So served at least 3 bars or manufactured by Pete's. Here's the solution. Select beer. So if we have select beer here, we know we're going to have group by beer down here because we have an aggregate. So unless beer is part of this aggregate, which it's not, we're required to have the group by. So we got the group by down there. So select beer, average price from sales. Having, here's the new part, having a count bar is larger than or equal to 3, or the beers in select name from beers where manufacturer is equal to Pete's. So we got the beers manufactured by Pete's down here, and then up here we have the having counts. So it's an extra way of putting an extra condition in here. Where's the where? We have no where. So what you don't want to do is from group by, or no, from sales where count is larger than, put the subquery in there, group by beer, switching it around. So there's no where clause in the outer query. Instead we're using a having, and the having is sort of like a where the count of the bar is larger than or equal to 3, or the beer in is in this group here. So beers grouped with at least 3 non-null bars, and also beers grouped where the manufacturer is equal to Pete's. Having is one of those optional kind of things. You may or may not use it. It depends upon whether or not you think like this, or whether or not you'd use a where clause. So it's definitely, you have some options when it comes to putting these queries together. And there are some people that will not create a subquery. So you'll never use an in. Instead, you'll use other queries. And you can do all of these queries in multiple different ways. There's no right or wrong way of writing a query in terms of that. So assignment number 3, we'll have you write some queries. So before I get into the database modifications, inserting rows, deleting rows, and updating rows, which is different from running queries, I'm going to take a slight detour, take a look at the assignments. So assignment number, I believe it's assignment number 3, but let's take a look here. Yes, some important information about assignment number 3. In assignment number 3, I've given you, let me make this a little bit bigger here. There we go, much bigger now, it's good. It's 2 parts. We have figure 1, and then we have figure 2. And then we have 2 kind of sets. We have question number 1. It says specify the following queries in SQL on the database scheme in figure number 1. And part number 2, it says specify the following queries in SQL on the database schema in figure number 2. I have figure number 2 down here. So figure number 2 has got a table employees, table department locations, works on, project dependents. Table number 1 has multiple, figure number 1 has student courses, prerequisites, section, grade reports. So let me run through a couple of queries to give you some ideas about how you're supposed to tackle this actually. Because some of you will do this hopefully and turn it in before we come and see you again. So let me make this a little bit bigger so we can see the entire query here. Okay, so question number 1, A. I'm only going to do 1A for you. So you can put some spaces in here and just write the queries, type them in if you want. Retrieve the name of all senior students majoring in COSC, computer science. So I want names and I want senior students. So I come down here to the table. Let me make this a little smaller so we can see the table. Oops, that's way smaller. So in the student table, we see we have a student number. Now we have student name. Here's name. So from the where clause, the from clause, if I were writing this query, I'd write select from where. And then I come down here and say, what table am I looking at here? Probably the student table, because it's not going to be in courses, prerequisites, sections, or grade reports. Nah, probably the student table. So from student, what am I going to select? Name, because that's what it said. And what's the where clause going to be? It's going to say all senior students majoring in computer science. And this is what the code is for computer science. So I'm going to say where, and I'm not given any data, I'm just given.
You are actually, if you go to number D, yeah, in D it is, yeah.
Retrieve the name and the transcript of each senior student. Class is equal to 5. Yeah. Well, what I was going to say is there's two things here. You could rewrite A after you looked at D, or you can ad-lib it a little bit. What I'm looking for is the concept, not the exact. It's not like math. There's no right or wrong answer. But you're going to write a query. If you knew that the class was a number, because down here it's not really telling you. It says we have a name, we have a student number, we have a class. So class would be 5. So was that freshman, sophomore, junior, senior is only 4. I guess it could be something less. You can treat this like a text, or you could treat it like a number, depending upon the. So major. So the major is going to be computer science. So where the major is equal to SOCS, and we want all senior students who are majoring. And then we have class. You could say class is equal to senior if you wanted to. Or you can come down here and say, well, class is equal to 5, because these are the senior students. I don't care how you write it. I don't care if you ad-lib it and saying, well, let's just call them seniors, because I'm not giving you the data type down here. So what you want to do is you look at this as the resource. Write the queries that make sense, given the context you're giving it. So if you want to treat it like a senior, sophomore, junior, senior. And if you look over here, it says retrieve the names and transcripts. The name and transcript of each senior student, well, that's class is equal to 5, majoring in computer science. And a transcript includes course name, course number, credit hours, student year, and grades for each course completed by the students. Uh-oh. Then you got to go down here and go, well, there's a transcript. Here's a grade report. And look, it has a student number. And look, each one of the students has a student number. So then you have to figure out, well, that's going to join the two tables together. Or do you have to join the two tables together for that? No, actually, you probably can go from student, comma, grade reports, where something is equal to something, so that you can figure out how to list out what you're going to select. And can you probably select? Yeah, you can go student.name, or student.student number is going to be equal to grade report.student number, or section number, student number, and then the grade is going to be equal to this, grade is going to be equal to that. So use your creativity, academic creativity. Don't get harped on the, is King, Professor King, is that going to be the first name or the last name? So retrieve the names of all courses taught by Professor King. Well, we have courses here, and we have course name, course number, course credit, section, students. And where do we have instructor? Here's an instructor down here on the section. So is the instructor, is that instructor first name and last name? Or is their instructor just going to be equal to King? Just have instructor equal to King, is what I'm saying. So make it work for you. The idea is to have you see if you could retrieve the information. It's like a scavenger hunt with querying. So see if you can get the information out here. See if you can write those queries as the object to it. Now I will tell you that part A is pretty straightforward. First question is pretty straight. Part number 2, there's some joins with that. Do the joins the way you want to do the joins. You can probably get away with some of them without joining it. A couple of them may actually require a join, may not. You can run multiple queries if you want instead of doing the joins. If you're unfamiliar with the syntax of the join, use a join wording or a join syntax that you're familiar with from anything that you might be exposed to. If not, use generic the word join. natural join, cross join. Make it up. Make up the syntax. Or look it up online for a particular database. It doesn't have to be related to Oracle. It could be any database like MySQL. And you figured, oh, in MySQL you do the join this way. And you're going to use that syntax or that word. So in Oracle you can actually use a plus or a minus next to something. And you can actually do joins without using the word join, just by doing the thet on two table conditions where this table is equal to that table. Is it really doing a join? Yeah, but you're not doing a join. I mean, you're not using the word join, but you can do the join without the word join, if that makes any sense. So that's about assignment number 3, and again, academic dishonesty applies towards that as well. You don't want to copy off the internet. You can't copy these off the internet anyway. And it doesn't really matter. There's no right or wrong answer as long as the query makes sense for what it is you're trying to do. So, and you're using something here. There's actually, when you get down to the second part, there's a couple of different ways of interpreting a lot of this stuff. It depends on your interpretation as to how you're going to write those queries. If you write the queries and the queries look like they make sense, I'm going to give you full credit. If you don't write the queries, you don't get any credit. If you cut and paste queries that don't even match this off the internet, that's going to be a problem too. The idea is to get practice writing the queries. Questions on assignment number 3? Nope. All right, back to aggregates then, or back to database modifications. Here we go. Alright, so let's go down the concept of modifying. So now we've seen all the manipulation commands up here for querying. So SQL is also used for modifying databases. So the modification command does not return a result. Over here we usually get a result set that gets turned back. That says 5 rows, 6 rows. Well, we get on the database manipulation, we get how many rows were changed. On the query, we get a result set that comes back. So we're not looking for a result set anymore. So there's 3 kinds of modifications that can be performed: an insert, a delete, and an update. Those are modifying or changing the rows. So you can insert a row, delete a row, update a row. So actually now we're not going to create the table, we're going to populate the tables with some data. So insert a single row, you can go insert into relation. And what values are we going to insert? The values are going to be in the list. How do we know what order to put the list in? Well, if we save the notes on when we created the table, the way we create the table is the way we're going to put the list in. How are you going to remember that? You're not, so you're going to use a different syntax coming up next. But here's an example. To add likes and drinker, the fact that Sally likes Bud. So we're going to add to drinker likes, to the table likes, we're going to add Sally and that she likes Bud. And we have drinker and beer in here. The fact that Sally likes Bud. So insert into likes values, and in the values we're separating it by commas, and the commas are going outside of the quote here. We have Sally, comma, Bud because they're both text fields. We can't go Bud, comma, Sally because we created this table, drinker, comma, beer. It has to be in the right order that we put something in. So we have to specify the attributes in the insert. So we might add to the relation the names of a list of attributes. So there's 2 reasons why you want to do this. You're probably going to forget the standard order of the attributes for the relation. And the standard order is the order that you created them in. That's when you probably could remember drinker, comma, beer. But if you had like 20 attributes in there, you may not necessarily remember that. So you don't have the values for all the attributes perhaps either. What are you going to do in that case? Leave it blank? Just don't insert it in. If you put something in there, the default's not going to work. So if I don't have, let's say for example, I want to put Sally in, but I don't know what she likes. I don't know what beer I'm going to put in. And then the default in my query that I created the table with, I set the default as undecided. Am I going to remember to put that in? Nah, in fact, I'm probably just going to put a blank space in there when I put it in, and then now I'm not going to get undecided because I put a value in. And then I'm going to have inconsistency. So if I look up all the undecided people, depending upon how I put the row in, I'm not going to find Sally because she's not really undecided. She's empty. So you don't have the right values for the attributes, and you want to make sure the system will fill it in with the missing nulls or the default values. Then you can't specify a value for it. So here's the solution in specifying attributes. Another way to add the fact that Sally likes Bud to the likes table, where we have drink or beer, we can insert into likes. What are we going to insert into likes? We're going to switch the order. Beer, comma, drinker. And the values that we're going to put in for beer, comma, drinker are going to be Bud, comma, Sally. So I could just put in, let's say for example, beer, or just put in drinker and leave the other ones blank. And if I have default values set on the table, then the default value will be inserted into the table instead of whatever value I sent here. Well, didn't send here if I were to do it that way. So you're inserting into likes and you're specifying the order, and then you're specifying the values that you're going to put for that order. So you can also insert many different rows in. So you may insert the entire result of the query into a relation using the form insert into relation a subquery. If I do that, then I'm going to do insert into a subquery as an example using frequency, and frequency says drinker, comma, bar. Enter into new relation potential buddies, pot buddies, which is going to be a relation that we're going to have, and there's going to be a name of Sally's potential buddies, i.e. those drinkers who frequent at least one bar that Sally also frequents. So we can see who your possible friends are. Here's the solution. So now we have a new table called POT, or potential buddies, or pot buddies. I guess I should rename that one. The other drinkers here are going to be select D2 drinker from frequency D1, comma, frequency D2, where D1.drinker is equal to Sally, and D2.drinker doesn't equal Sally, and D1.bar is equal to D2.bar. Where are we getting these D's from? This from the select. So what do we got here? From, on the from clause, if I start with the from clause, I can always eliminate all of my confusions normally. I can go from the from clause from frequency D1 and frequency D2. So I'm doing a query on the table to itself because I want to find where Sally drinks beer, those bars, and then also find where other people, not Sally, but other people like the same beer and they drink at the same bar, or other people like to frequent the same bar. So here's a pair of drinker rows where the first is from Sally and the second is from somebody else but not Sally. And the bars are the same. So I can find my potential buddies for drinking in bars. Not that I need to do this, but Sally might need some help finding out, because she's blind and she doesn't see who's in the bar with her. So we're going to take it from the database. So
the table was not defined, so the select statement automatically creates the table.
You have to imagine that we created the table. Yeah, you have to imagine that we created this potential buddies table, and that the potential buddies has in it name, just names is in there, because we're gonna only pull out names out of here. So we're gonna insert into this table we just created. What are we gonna insert into? And here's the opening and the closing bracket, and it's gonna be the query result. And the query result's gonna be selecting D1.drinker. So we're gonna select, D2 drinker. So we're going to select the drinker name where 1 and 2, from 1 and 2, where 1 is equal to Sally and 2 doesn't equal Sally, and the bars are the same. So it gives us the names that come back. The names are going to come in here, and it's going to be the other drinkers, and it could possibly be more than one. It could be like 5 different people. And because this table looks like this, the new relation looks like this here, it just has a name in it, so, which is how the query works. Comes in handy when you want to get query results from how many books by this author, and what other books, like you find an author and you're at barnesandnoble.com and you're searching. You might create a temporary table that holds the results, or a temporary results set that comes out of this, and the results set's going to have all the books by the same author. And then you find this book and says, well, what else has this author produced? So people who liked this book also liked all these other books. Well, there's a database in there of all the people that purchased this one along with all of these other ones. So it's just going to query it and say, well, if the person bought this book, what did the other people buy along with this book? Which is a very similar, here's your potential next purchases or things that you can add to your order in terms of the concept. I hear a class in the hallway. The attendance people must be making their rounds. I'm looking at our clock going, is it time for our attendance soon? I'm looking at the door too. All right, deletion. Oh, we have a note here. Hold on 1 second. Let me pause this for a second. Okay, we're back to the lecture. If we could keep it down a little bit, that'd be nice. So we were talking about deleting. We stopped on deletion. So to delete rows satisfying a condition from a relation, we use the delete. So delete from relation, where. Now on the delete, we actually have to remember to include the where clause. If we leave the where clause out, we'll delete the entire relation, which is not such a good error to come up with. So here we have delete from likes drinker, comma beer, the fact that Sally likes Bud. Sally doesn't like Bud anymore, so we're going to delete her out of the table. So delete from likes where drinker is equal to Sally and beer is equal to Bud. We'll delete all of the records. Now when we do a delete, it's should also mention that there's rollback information. If we do a delete, or if we do any of these operations actually under the DML categories or the DDL, depending upon the operation, and everything we've talked about so far contains rollback information, which means we delete that Sally likes we delete from the likes table that Sally likes Bud, and then later we decide that, well, Sally really does like Bud, so we don't necessarily need to put her back in. Instead, we roll it back. We type in the word rollback, and it'll remove the, it's like an undelete or undo command. We could delete all rows by simply leaving out the where clause. So make the relation empty, which is delete from likes. And we forgot the where clause, so no where clause is needed. We forget it, we delete all the records in there. Have we deleted likes? No. Likes still exist. The table still exists, but the records inside of the table, all of them are gone. So it's kind of dangerous to do that, actually. We can also delete many rows instead of just one row. If we delete many rows, we can delete from beers, name and manufacturer, all beers for which there is another beer by the same manufacturer. We want to get rid of the duplicates. So if there's a beer in there and it's by the same manufacturer, and there's another beer in there by the same manufacturer, we can delete it. So the beers with the same manufacturer and different names from the name of the beer represented in row B are going to be deleted. So delete from beers, and we have the from clause here, delete from beers B, where there exists, select name from beers where manufacturer is equal to b dot manufacturer and name doesn't equal name. Same query we saw earlier, actually, same subquery we just saw a few minutes ago. But now it's being used in the context of the where. So where exists, and then we have from beers along with delete. So the delete from is actually in the replace of, because we have no select in this case. So there's nothing in that we're going to put on the top. There's no select anything. It's just going to be a from, delete from. So in the semantics of the deletion, suppose Anheuser-Busch makes only Bud and Bud Light. And suppose we come to row B for Bud first. And the subquery is not empty because Bud Light rows exist. So we delete Bud. Now when B is the row for Bud Light, do we delete that row too? Well, are we going to find that there's a matching row? Or is it going to come back? So the answer to the question is we do delete Bud Light as well. The reason is that the deletion proceeds in 2 steps. We mark all the rows that we're going to delete, then we delete them. So mark all the rows for which the where clause is satisfied in the original relation, and then do the delete. It's kind of like the same concept that works with the from and the select. If we're going to do a delete, it goes second. So we mark the rows that we're going to select, then we select them. In here we're going to mark the rows we're going to delete, then we're going to delete them. So it's after the entire query has run that we've analyzed all the different results, then we're going to delete it second. Just the same way as after we've found the matches, then we're going to produce the selection that we've selected out of that. So we delete the marked rows. Which is interesting because it'll finish the query results before any deletion occurs, so we'll find all the matches. So it always happens secondary. We can also update a query, update a relation, excuse me, to change the certain attributes in the certain rows of the relation. So we update space the name of the relation. We set a list of attribute assignments where some condition on some row exists. So the where is always using a condition. The update is going to be some relation that we're going to update, and we're going to set something. So here we're going to change the drinker Fred's phone number to 555-1212. So we're going to update drinkers. So it's kind of like the same semantics as the delete. So, or excuse me, from. Delete from. Update drinkers, name of the table. Set the phone number is equal to 555-1212, where the name is equal to Fred. So we've got a particular where condition, name is equal to Fred, and then we have the phone, 555-1212. So that's how the update works. We can also update several roles at a time, and then this again is kind of dangerous as well. Sort of like the delete from this table, that's kind of dangerous. Well, this is dangerous because we can update all the rows in the table accidentally by leaving out the where clause, or update everything. So make $4 the maximum price for beer. So we can update cells, and we can set the price to equal $4 where the price is equal less than $4. So if we just did this, and we left out the where clause, and we said update cells, set price is equal to $4, every single row in that table is going to be now $4. So you can see that's kind of dangerous, actually. So it's kind of like the delete. So people make mistakes all the time. You would just roll it back. You say, okay, sorry, wrong thing. So we have some more SQL statements to look at. We can define the database scheme and the views using SQL statements. So this is the more interesting part of it. We saw earlier some create table commands, and we're going to go through the semantics of this and the pieces of it in a little bit more detail now. In terms of defining the database scheme, the database scheme comprises of declarations for the relations or the tables of the database. So we're defining the tables. Many other kinds of elements may also appear in the database scheme, including views, indexes, triggers that we're going to see later. So we probably won't hit triggers today. We'll probably hit it during the second weekend. Stored procedures and triggers are going to be the theme for next time, so one of the themes. So we can declare a relation, create a table. Simplest form is in this format here where it says create table, give it the name of the table, and then list out the elements. And you can also remove a relation by doing this, drop table. Drop table gets rid of it, and you can roll it back. You can actually get it back. Truncate table gets rid of it permanently, no rollback information. Why do you want to do that? Tables are big. And you want to get rid of a table, you're going to drop a table. You're going to have all that stuff stored in memory, and then you're going to recreate the table, and then you're going to put all the data back into the table. You're going to have the database run a bit slow for a while until you commit or roll something back. If you just want to get rid of it, you know you're never going to use it again, then you truncate it instead of dropping it. It's just the same thing, actually, except for there's no rollback information. So there's no temporary data being stored for it. So you remove a relation from the database scheme by saying drop table. It's the safer command, but it keeps the rollback. Elements of the table declaration. So the principal element is a pair consisting of the attribute and then the data type that's going to be associated with the attributes. And then that's when we can also specify primary key, foreign key, and unique, and not null and null. They go along with each one of the attributes. Most common types, as we've seen before, are int or integer or number. You can use numbers. And again, the data types are going to be specific towards the database, just like the join commands and the aggregates. They're going to be labeled differently for each one of your database vendors that are going to essentially provide you with this capability. So reals, floats, integers, ints, characters, variable characters are all your different variations. And we've actually gone through this a little bit, so we can just see the examples. So we're going to create these beer and bar tables using create statements. So create table cells, and it's going to have bar in it, and bar is going to be a character of 20 character spaces, and then we're going to have beer, and that's going to be a variable character of 20. Only difference is the number of padding versus not padding that we're going to get. Remember, the characters don't pad, characters pad, variable characters don't pad. And the price is going to be real. It's going to be real number. Now, this syntax is going to vary depending upon the vendor. This might actually be number instead of real, the word number. So, and again, it does not have to be capitalized. The capitalization is for illustrative purposes. So. Dates and times. So the date and the time are types in SQL, and they form the value here in terms of the date by default, year, month, day. So the example, the date is 2006 0704, or the 4th of July 2006 is what this looks like. So time as a value as well. The form of the time is hours, minutes, and seconds. So an optional decimal point for fractions of seconds can also be used. As an example, 0.5, 0.6, get down to microseconds. Or equals 2.5 seconds after 3:30. It's going to be 0.5, 2.5 I should say. We can also declare keys when we create the tables, and so an attribute or list of attributes may be declared as a primary key or unique. So these stay as attributes, so you declared the functionality determined by all the attributes in the scheme, and there are two distinctions to be mentioned later between, and actually I already mentioned them, whether you're going to define the keys while you're creating the table, or you're going to do it after you create the table, and then are you going to say unique, or are you going to actually define it as a key, depending upon whether or not you want the indexes created. Declaring single attribute keys. So here we go. Place primary key or unique, the word unique or primary key, and notice that they are two separate words. Primary key is and unique are similar, but unique is not indexed, and you cannot create a foreign key out of a unique. You can only create foreign keys from primary keys. So you just put the words after, and here it is here. This is what I was saying before. In the other examples that I showed you, you could skip all of the named constants. You don't have to name the constant expression or the constraint. You can actually just use unique or use primary key. So create table beers, name character unique, comma, manufacturer character 20, character 20. So the name and the manufacturer are both characters, and name is unique. And we put the keyword unique next to the data, right after the data type, actually, in this example. Doesn't make it a primary key, it just makes it unique. Or we could declare multiple attribute keys. So a key declaration can also be another element in a list of elements of the create table statement. This form is essential if the key consists of more than one attribute. So we have multiple valued attributes, then we can name them as separate keys, and can be used for more than one attribute key. Here's an example where we have bar and beer together as a key for cells. So we have a multi-attribute key, and then now here on the bottom we're going to add it as primary key bar comma beer. So create table cells with the column called bar. That's a variable character. That's a character. Beer, that's a variable character. Price, that's a real or a number. Imagine that these data types are going to change depending upon the database vendor that you're using. And then remember, before I said you don't have to give it a name. You can just say primary key, foreign key. And what we're listing here is the primary key. And the primary key is going to be a bar beer combination. So that's going to be added to the table as a combination, as a composite, multi-valued attributes. Or if, let's say we wanted, in this other example up here, we just wanted one of them, like that's the unique, but let's say we just wanted, one of them up here I think had the name as the primary key. you can just put primary key next to the name, and you've turned it into, instead of unique right here, actually you can just put primary key here, then the name would be primary key. So you're specifying that the attribute column is a particular primary key. So primary key versus unique. SQL standard allows databases implementers to make their own distinction between primary key and unique. As an example, some database management systems might automatically index the primary key, create an index data structure to speed up the search in response to primary keys, but not unique, which is the case in Oracle. So if you don't want the index, you make it unique. Then you get pretty much the same thing, except for the fact that you can't make a foreign out of a unique key. Foreign key can only be made from a primary key. Another required distinctions, however, standard SQL requires 3 distinctions. There can only be one primary key for a relation. If you already have a primary key in the relation and you want a secondary key, then you make it unique. But that practice is not what I'd call very standard. You don't want to search on that unique key. If you're going to put a unique key in there, you're going to put it in there because you don't want duplicates, and you only want them in there for one major, or you only want them in there for one thing, then you make it unique. But it's not going to be for searching purposes. No attribute of a primary key can ever be null, but attributes declared unique may have nulls, and they may be several rows with nulls in them. So you might not have a value for it. As an example, you put a student in the database and they have a student number, student ID, but you have passport number and social security numbers. So you could have a column that says social security number and you can make it unique. And because everyone's supposed, you don't want to have the same social security number for multiple people. But you're not going to be using it as a search field because it could be null. It could be null because they might not have a social security number. You might be a foreign student, but you have a passport number. And then the regular American students that are in there are going to have social security, but they may not have a passport number. If they haven't applied for a passport yet, they haven't traveled yet, then they may not have that. So they're not going to have that. But everyone's going to have a student ID, theoretically. So unique is not used as a primary key, because primary keys, you can't have a null for a primary key. But you can for a unique. It's empty. It doesn't follow the same rules as the primary key. Other declarations for attributes. So you can say that a column, you can make it unique, not null. Which means it's almost like a primary key, but it's not. It's not null. So other 2 declarations that can be made. Not null means that the value for this attribute may never be null. So if it's not null and it's unique, it's pretty close to being a good primary key, except for it's not indexed. But you could index it. So you could create a primary key. You can create a unique key that's not null and then manually create an index on it. And then technically you have 2 primary keys. Why do you want to do all that? You're going to add confusion. You're only going to do it if one application is stuck on using passport number as the primary key, and you have to join that table with another one, and it always uses passport number. And you have to and you want to make that so it's more, it adds more constraints. Then you put on the unique, and then you put on the not null, and you index it, and it looks and acts and kind of feels like a fake primary key in that case. It's a workaround. By default, just make it a primary key if it's supposed to be a primary key. And also the default values we've seen before says that if there's no specific value known for this attribute's component in some row, use the stated value instead. So here's an example where we have, here's our primary key in here as well. Create table drinkers, and the name is going to be the primary key, and the address is going to be this length, and by default it's going to be 123 Sesame Street if nothing's not in there. And you can string all this stuff together. So in here I could put not null, unique, default all together and really constrain this address. So we can't have people at different addresses, or no 2 people can have the same address. It can't be null. If you don't put anything in, well, isn't default gonna outweigh your null. So there's no need to put the null in there then, or the not null, because the default's always going to go in there instead of the not null. So some of it, might be overkill, I should say. So you want to go down to the minimum of what you need for each one of the columns, making logical sense out of it. So the effects of the default, in this particular case, the 1, 2, 3 Sesame Street, suppose that we inserted the fact that Sally is a drinker, but we know neither her address nor her phone number. Then the insert with a potential partial list of attributes makes the insertion possible. We don't know it all, so we're going to put in just her name. So insert into drinker's name values Sally, and then the rest of it will be put in by default, because here for drinkers we have we're going to have default 1, 2, 3 Sesame Street, and because phone number here doesn't have a default, it's going to be null. So we're going to come out with null for it. So if we look at the results here, we see, but what appears in the drinkers table is the name Sally, the address 1, 2, 3 Sesame Street, and then the phone number is null. So if we had declared phone number is not null, then the insertion would have been rejected. By default, most of the table creation tools will make everything not null and have you change it to null, which is kind of counterintuitive, because it's going to make it so you're noticing if something is null. So it's actually probably a good feature that they do it that way. Now after the table has already been created, we can alter the table to add more stuff to it. If we're going to alter the table, we might change a relational scheme by adding a new attribute or a new column. By going alter table, the name of the table, add an attribute declaration. So alter table, here bars, add a phone number, and the phone number is going to be defaulted as unlisted. Why are you going to do that? Because we're going to have everybody in there who is already in the table who's now going to see unlisted instead of empty. So we're going to have unlisted listed there, which is nice, but really is it unlisted? Then we have to update everybody's telephone number. So this happens when they add something like the email address to your customer profile, and you call in and you say, hey, I'm not showing that you have an email address in the system. Would you like to put an email address in? Because then it says, instead of unlisted, it says need to ask about, or need to get, or please update next time the customer calls in. So when you look at the record, it comes back with this default. It says needs to update, or never given. Then let's ask them, and then we change it. So it gets updated eventually if you call in for support or something. We can do the opposite. We can actually delete rows out of it. So we can delete the attribute as well. So we remove an attribute from the relation, alter table, give it the name of the table, drop the attributes. Here's our example. We don't really need the license. We put a license in here for the bars, but have we used it in any of the queries? No. What do we need the license for? So let's remove it. So we alter table, bars, and we drop license. So it removes it. Only problem with that is you got to do an undo in order to get it back, and then that operation is kind of risky. So it's not a bad idea though to drop unused fields, because in each one of the records it adds an extra space, adds an extra component that you might be saving that you don't really need to save, and it's going to make the table a little bit bigger in size. So let's talk about views, last but not least on our list of items to create here. So the view isn't a table, it's a virtual table. So it's a virtual table, it's a virtual relation that's defined in terms of the contents of the table, or more tables. So you create the view, you give it a name, and it's as a query. So create view drinkers, or my drinkers, as select star from drinkers. And then you got everybody. Why don't you just use drinkers if you're going to do that? So usually it's a query that's going to have some where clause to it. In contrast, the relation whose value is really stored in the database is called the base table. So that's where the word base table comes into place. It's the base table, and then we have a view that's created on one or more base tables in concept. Here's an example of our view definition. Can drink. So we're going to create a view can drink, And the view can drink is going to have drinker and beer in it. And it's a view containing the drinker beer pairs such that the drinker frequents at least one bar that serves the beer. So create view can drink, and this is going to be as select drinker, comma beer from frequents, comma sales, where frequents.bar is equal to sales.bar. So these are drinkers that frequent at least one bar that sells their beer, which means they can drink at that bar. What does this give you? This gives you a view that's not a table, that you haven't changed any data and you're not storing any data. The underlining data is coming from the underlining tables. However, it's already pre-configured for you. So now you just query the can drink. You query the view as if it were a table. So you can select star from can drink or drinkers equal to Sally. You can get all of Sally's information out, but it's really a combination of drinker and beer, frequents and sales that came out of, and you got drinker and beer out of frequents and sales. So it's a subcomponent that only contains the information that you're interested in looking at. So accessing a view, you can query a view as if it were a base table. It is a limited ability to modify the view if the modification makes sense as a modification of the underlying base table. Here's an example. Select beer from can drinker where drinker is equal to Sally, as I mentioned before. That's a way of querying the view. What happens when the view is used? Not so efficient. So the database management system starts by implementing the query as if the view were a base table. So it's going to run the query like you're going to run a base table. Typically it turns the query into something like a relational algebra expression. The queries defining any view used by the query are also replaced by their algebraic equivalents and spliced into the expression tree for the query. So it's a little bit more optimal than running two queries, one right after the other, but it's almost the same. You have a little bit of efficiency because you're going to slice into it. Here's sort of what it looks like. So in the view expansion, you get the projection of beer, where you're going to select drinkers equal to Sally. And then now you've got the can drink view. And well, the can drink view is really a join on frequents and cells. So it's going to do the join for you, and it's going to slice out the view information from it. So the view is a slightly more optimized version of running the two queries separately. But every time you do a query on a view, you're still doing the join. So you have to create the view in order to do the query on the view. View doesn't stay. It's not created in the database. It doesn't stay in memory. It's a concept. So it's a virtual table, not really a table. Nothing actually gets created. You're predefining a query that you can run the query on the query over and over again without actually hitting the base tables, without touching the base tables. It's a protective mechanism. It's only going to get, the view is going to give you a subset of the underlying tables. It isn't going to give you everything. So is it more efficient? No. It's more efficient to run it on the base tables. Is it safer? Yeah. So let's talk about database optimization for a moment. Interesting to observe that the typical database management system will then optimize the query by performing an algebraic expression to one that can be executed faster, which means it can do the join on the indexes, which is why when you do a join on the keys and the indexes can be used, you've got a more optimized query. So a lot of what you get with Oracle and what you get with paid-for databases is more optimized queries. The queries run faster because there's more logic, there's more research, there's more implementation. It's mostly proprietary optimization that's being performed to make things run faster and more efficient. A lot of your cheaper or your free databases, MySQL has no query optimization. So a lot of people have done some work on it, but it's user supported. There's no driving factor to make that query any more optimized. It works, but it's not cutting edge in terms of its optimization capabilities. So the key optimizations, you want to push selections down the tree, make it happen last, And eliminate unnecessary projections. If you don't have to join it, don't join it. Get rid of the unnecessary projections that are going to occur. So if we were going to optimize this here, we have in the optimization here where we got the projection on the beer. We're going to join the drinker on the select drinker is equal to Sally. Instead of joining the entire table, join it on the condition. If you're running the projection of the condition, you have fewer records. So if you're going to do that, then you're going to push this up the tree, excuse me, push the join down the tree and the selection down the tree. So at the end, after you've gone through all of the different subsections of what you're looking for, then you're going to join that part of it and select from that. So you have fewer records, essentially. Notice how most rows are eliminated from frequency before the expensive join operation occurs. Get rid of the ones that you're not working with. Don't join the whole thing. So there's people that will write queries that will join two tables together, then run a query on it. It's like, why? When you don't have to. So weed out those records that you want, get what you only want, and join that. Is there any more SQL? There's certainly a little bit more. Oh, there's always more. Foreign keys, local and global constraints. So foreign keys and constraints, we've actually looked at constraints, key constraints actually. A constraint is a relationship among data elements that the database management system is required to enforce. In the form of a key constraint, it's on the key itself. That's what we get with primary and foreign keys. If we want to enforce the constraints, we can't do it with just primary keys. Primary keys just gives us nothing more than a unique key that is also indexed. So we have to pair it with a foreign key. So you're half done if you've created primary keys in every table. You link it and you create the key constraints with the foreigns. So a primary key in one table is a foreign key in another table. So the keys give you the key constraints, foreign key, or what some people call referential integrity. It's referential integrity when one key from one table references one from another table. Any change to one affects the other. So there's integrity checks that are performed on all operations. Does it make the database run slower? Nope, because it's optimized in the system. And the key constraints actually add to the consistency of the data. Make sure that we have matching entries in both tables. Make sure everything is consistent. It makes it harder to put data into the tables because you have to follow all of the constraints and all of the rules in order to get the data to actually be inserted properly. So value-based constraints, constraints that are based on particular attributes, like the M or the F example I gave you earlier. And then row-based constraints, relationships among different components in the row. Can we put a graduate student into the computer science database and they're taking healthcare management classes? The registration on that is going to fail because we can look at that and go, this student is taking that. Oh, no, not going to work because of the row itself. It's not going to meet certain conditions. And then we have this concept called an assertion. So any SQL Boolean expression is an assertion. We can create an assertion, run the insertion on a check. And what we're doing is we're checking the value of certain things in the row to make sure it's consistent. Like a graduate student who's already completed their degree and they're registering for classes. So it's violating the logic or it's violating the information that we've set out for the rules. So consider the relation cells, and cells has bar, beer, and price. We might expect that a beer value is a real beer, something appearing in beers.name, hopefully. And we want to make sure we have sales. We're not selling beers that don't exist. So we have a foreign key and a primary key matching. So the constraint that requires a beer in cells to be a beer in beers is called the foreign key constraint. So that's why the word references is used, because we're creating referential integrity. So the expression for the foreign keys, we use the keyword references. So either within the declaration of the attributes or when one of the key attributes is involved, an element of the scheme is used to reference. So the foreign key with a list of foreign keys or references references a relation along with the attributes that it's referencing. So the reference attribute must be declared primary or unique, which is interesting because some databases actually don't allow. I don't believe Oracle allows you to have a foreign key that is on a unique and non-primary, which ruins the referential integrity. But some databases allow you to do it if it's unique, which is kind of odd, I think. So here's some attributes here. So with an example with an attribute. So we're going to create the table beers, which we have to create first because it has the primary key in it. The primary key is going to be the name. And then we're going to create the table cells. And then the beer here is going to be referenced. So we're going to have a column named beer, and it's going to reference beer's name. So we could have called it name, but instead we called it beer. So the name of the column that we're creating is called beer. But it references beers, this beer up here, this name up here, which is a primary key. So this is technically the foreign key by referencing. By creating this reference, we have a foreign key in cells that matches the beers, which means this name has to match this name. If it doesn't match, we can't put the row in. We're going to get the row rejected, which may not necessarily be a good thing. It makes it harder to put. It makes it much harder to put the row into the table. This is when using with an attribute, and the attribute that we have down here is beer name. We can also set it as an element. When we set it as an attribute, we're saying that beer references beers. We're not adding an element. We're not adding a column in. More efficient, yet less control over the column. You can't search on the foreign keys. It's not in there. It's just a reference. You have to search on beer knowing that that's a reference to primary key. So as an element, you add it in here where you've got table beers, table cells. Same thing as before where you got the name here, and the name is going to be a primary key. But then we're going to add a foreign key beer, and the foreign key that we're adding in here references beer's name. So it's put in as an element as a foreign key. So as an element, we're actually specifying, and the only difference here is we're specifying it as a foreign key. So now it's a key. Instead of a reference, it's actually a key, and the key is still a reference. It's still referencing beer's name. Just two different ways of doing it, two different syntaxes. So, enforcing the foreign key constraints. We can also tell the table how we want to enforce it. We can cascade changes. We can delete changes. We can basically determine what kind of behavior we're going to do when we try to remove a foreign key or change a primary key that has a foreign key associated with it. So if there's a foreign key constraint from attributes of relation R to the primary key of relation S, two violations are possible. An insertion or an update of the primary key R. Introduce values not found in S. And S is the primary key part. So we've introduced a foreign key value that's not found in the primary key. Maybe it's a spelling. Maybe we misspelled it when we made it into a primary, but now we're adding it as a foreign and it doesn't match. Or we delete or update the primary, causing some rows to be dangling. Or we deleted the primary, now we have dangling foreigns that don't match the primaries because we deleted it. Action number 1, suppose R is the cells table and S is the beers table. An insertion or an update to cells that introduces a non-existent beer must be rejected. A deletion or an update to beers that removes a beer value found in some rows of cells can be handled in 3 different ways. So we have to reject non-existent beers. If we have a removal, there's 3 possible ways of dealing with it, and we can tell the database what we want to do with it when we create the table. So 3 possible ways to handle the beer that suddenly ceases to exist. As a default, we can reject the modification. That's the default for Oracle. So it rejects it on a mismatch on an update, it rejects it on a deletion. Or we can cascade it. what does that cascade mean? Make the same changes in cells. So one change in one table changes everybody else. Not so desirable when the change is wrong. Maybe it should have been rejected, but we changed it anyway. So that's kind of you have to be careful with that. You could delete the beer, deletes the cells row. The entire row gets taken out. Or you can update the beer, change the value to cells. Or you can set it to null, changing the beer to null. And then now you've taken it out, you've left the row, but you've changed the value to null. So they call it cascading. So suppose we delete the bud row from beers, then delete all rows from cells that have the beers equal to bud. And suppose we update the bud row by changing bud to Budweiser. We change the name bud to Budweiser. Then we can change all the cells row names to bud so that it also says Budweiser on it. We can cascade it, yes? Excuse me? Oh, yes, of course. No problem. Thank you for asking. You don't have to ask, though. Anybody else, you don't have to ask. But thank you. I'll see you next weekend. And if we set it to null, not next weekend, 27th, 28th, yeah, you know what I mean. Let's set to null. Suppose we delete the bud row from beers. We can change all of the rows and cells that have beers equal to bud to have it equal to null automatically. So this is basically behavior that we can program into the table so that when something of this happens, automatically the tables deal with it certain ways. And we can put it table by table. It doesn't have to be all tables that are associated with. So suppose we update the bud row by changing bud to Budweiser. The same change can actually be occurring. So to choose a policy, we simply state it after we create the table. So we say when declaring a foreign key, we might choose to set null or cascade independently of deletions and updates. So following the foreign key declaration, we can say on update, comma, delete, or on update, or on delete, or on both. Then set to null, or set to cascade, or set to null and cascade, depending upon whether we're doing an update or a delete. So two such cases may be used. Otherwise, the default is to reject it. So if we have a problem, an inconsistency, then by default we reject it. On the foreign key, we can set, on the key line, we can say on update, cascade, or on delete, set to null, or one of the above actions. Here's an example of it. So now we're going to change the table around. So we're going to create table cells, and it has bar, beer, and price. And we have a foreign key beer. This is the same as we saw before, setting the elements. Foreign key is beer. It references beer's name. That was way up there. This is the cells table. And in the beers table we have name. On delete, set null. On update, cascade. That's pretty typical. So if you're going to delete it, then in the beers table, set it to null. But if you're going to update it, you misspelled it, you want to update it to make it capital B or something, cascade the change so it gets changed everywhere else instead of rejecting it. Otherwise, just reject it. If you left this part out in the previous examples, it would just reject it if there was like an inconsistency. If it's a foreign key, it must match that primary key. It gets rejected. If it doesn't match it, or we're doing an operation that's deleting it, then we're going to deal with it separately. You don't have to do both. You can actually just specify one if you want and leave the other one so the other one gets rejected. Whatever you don't specify gets rejected.
So the on delete set null basically is
On a deleting of a row out of this table, set it to null.
set null to
Yeah, if we're going to delete this foreign key in the parent, set it to null. Kind of dangerous. Excuse me, on the delete of the parent, set the child in cells to, if this parent beers gets, if we have a beers table and it has the name Bud, and we remove Bud, but we still have bars that sell Bud here, set it to null, because they don't exist anymore. Otherwise, you can't delete a primary key that has a foreign reference. It's going to reject it. If you try to delete the primary key, it has a foreign reference. The foreign reference is going to be non-existent, set it to null. If you delete the foreign reference, there's no problem. Primary already exists. You can delete foreigns all you want. It's when you delete the primary that you have to deal with it.
so these delete and update is
On the beers, yeah. It's to maintain the foreign key reference. It's if you delete the primary, then in this table it's going to set it to null because there's no more bud or something.
And an update foreign key child table. What happens if you update the child table?
If you update the child table and it doesn't match, the foreign key doesn't match the primary key, then you can cascade it. If you delete a foreign key, it's not going to affect the primary. Yeah, that part's true. If you delete the primary, what are you going to do with the foreign? Set it to null.
What happens if you update the foreign key which doesn't match?
Then you can cascade the update. So on the update, you cascade it. So you change the primary to match the foreign. It changes everybody. So excuse me, you're right. It will be rejected. You can't change from a foreign, you can't change the primary, but from the primary you can change all of the foreigns by an update. The behavior works downward from beer's name. Downward as the reference is where the confusion. Yeah, the way I was saying it it sounded like it was working the opposite direction, but you're right. It's working backwards. It's from primary to foreign. And it's to get the referential integrity between the primary and the foreign, which is basically to maintain the foreign integrity is what we're concerned with. Yeah. Attribute-based checks. So you can put a check on a constraint on a value of a particular attribute. Make sure it's an M or an F. And here we're using the word check on a condition. So it must be added to the declaration of the attribute so that when items are put in, just like the default, if there's no value, then the item as a default would put it 123 Sesame Street. So here we're going to check the value that we're going to put into this attribute. Make sure it's an M or an F, or it's what it's supposed to be. It's larger than $5 because we can't sell beer for under $5 or something. So it must be added to the declaration of the attribute. So the condition may use the name of the attribute, but any other relation or attribute name must be in the subquery. So let's take a look at an example so we can see what we're looking at. So the table sells, and we have a bar, and we have beer. And then on the beer, we're going to check to make sure the beer here is in select name from beers. It's in the beer name. Because we don't want to put beer names in here that don't match, but they're not keys. So we can still use that referential integrity without using keys by using a check. So on the beer here, we're going to check to make sure, this is going to come back true or false, check that the beer is in select name from beers. If it's not, if this check fails, then this row will be rejected. Oh, can't put it in. Sorry, Charlie. It doesn't match. And then down here, we're going to check here. Check that the price is smaller than or equal to $5. We don't want to sell beer for more than $5. Otherwise, we can't put it in. So you can't put the row in here if the price in the cells is higher than $5. It can equal higher. It has to be higher than or equal to. Smaller than or equal to $5. Can't equal $5. So the timing of the checks. An attribute-based check is checked only when the value of the attribute is inserted or updated. If it's not being inserted, not being updated, but it already exists in the database, the check never gets performed. So you have data in this database, and you put this nice little check on it. New rows after that will have the check. All the existing rows aren't being checked. So it doesn't constantly go through and check, only on an insertion or an update. So here's an example here on a check. Price is smaller than or equal to $5. Checks every new price and rejects it only if more than $5. And this example on the check is what I just did before. Not checked if the beer is deleted from beers. So if the beer, select name from beers, is not checked if a beer is deleted from beers, unlike the foreign key. So one of the advantages you have of using the primary foreign key is you have that referential integrity that goes on between the two of them. And there's always a consistency check. With a check of a check, there's no check. So you could put in beers, going back to here, that existed in the beers table at the time that the insertion created, but the beers table removed the beer, but it's still showing up in the other table. Because it's not referential integrity, it's just a check. When it was put in, we had that major. Now we don't have that major anymore. So we actually had that in the ITU database. We had students with majors that didn't exist. So what's your major? I think it was industrial management or something. Industrial. We have engineering management, and then we had industrial management. We don't have industrial management, but we have industrial management majors. How do we get that? We don't have that degree here. Or healthcare management at one point was a major. Now it's MBA with healthcare management. So engineering management now encompasses industrial management as well. But it's not reflected in some student records, actually. They have degrees in these majors we don't offer. So, which didn't check some of the government stuff, too, for BPEBs or whatever. I don't know what the whole thing is, but it's inconsistencies because it's not a key. There's no foreign, primary, referential, anything going on with that. Instead, it was just maybe there was a check, maybe there wasn't a check, but who knows. Row-based checks. So we're going to check values in multiple different columns that are in the row before we let the row in. What does that mean? We have a check on a condition. May be added as another element of the schema definition, and the condition may refer to any attribute of the relation, but any other attribute of the relation requires a subquery. Checks on inserts and updates only. So inserting and updating. Here's a row-based check. Only Joe's Bar can sell beer for more than $5. So we have to check to make sure the name is Joe's Bar if we're going to allow the beer to be higher than $5. So create table cells. And then we have the bar, the beer, the price. And then we have a check. So the check is being put in as an element. And the element here is if the bar is equal to Joe's Bar or price is smaller than or equal to $5. So Joe's Bar passes. Okay, we're good. Can we keep the noise down in the back? I can't talk over the conversations that are going on. Thank you. Or you may also feel free to leave okay. I just don't want to keep it's irritating people, including me. All right, so the check is going to be for the bar is equal to Joe's Bar, which is going to pass. Or so if the price is higher than $5 but it's Joe's Bar, then it's going to pass. And how do we know that? Because of the name bar, which is the check on another attribute. So it's a row-based check. We also have this concept of an assertion. So these assertions are based on the database schema elements like relations or views. We create the assertion just like we create a view, and then we apply the assertion. So we define here create assertion, give it a name, and the assertion is going to be a check. So instead of putting the check on the table, we make the check into an assertion. We run the assertion anytime we want on the table. Usually the assertion is going to be run when a condition exists. So the condition may refer to any relation or attribute in the database schema. Here's an example of the assertion. In sales, we have bar, beer, and price. And no bar may charge an average, so we got an average, of more than $5. How are we going to find an average? We can't do that. I guess we could do that on a row inserts. And we can find an average, and then we can reject the row. Or we can create an assertion. So we create an assertion, no rip-off bars. And the no rip-off bars does check. And make sure that there's no existence of selecting a bar from cells grouped by bar having $5 less than the average price. So the bars with an average price over $5 is going to come out of here. And so we're going to have a non-existent, can't be more than $5. So the check is to make sure it's not more than $5. We call it no rip-off bars. So we run the assertion to see if that exists, to see if the condition is there. Here's another one here, in drinkers, the name, address, phone number, and bars, which is name, address, license. There cannot be more bars than drinkers. So the assertion would run and say create assertion, few bars, check. And that would be select count from bars smaller than or equal to select the count from drinkers. So assertions are usually run on multiple relations to check for certain conditions that we want to we want to create the condition where we don't have any rip-off bars and we don't have more drinkers than we have bars. We're the government and we're trying to control the number of bars, and then we're trying to figure out, well, we want the count to be less or more.
They act as constraints.
They're not. They could be put in as constraints, or they can be. Here's the timing of the assertion. This is going to answer your question right now. Actually, the timing of the assertion checks. You can put them in principle. You must check every assertion after every modification to any relation in the database. So they can be put in so that upon an update or an insertion, the assertion check actually runs. And if it runs, then it triggers and says, oh, can't put the row in. If you put the row into the table, it's going to violate the average price because it's going to raise it high. It's kind of like what ends up happening when a student gets on academic probation. When the GPA drops before a certain point, if there's an assertion in there, then the assertion comes back and says, oh, can't graduate. Can't graduate, why? And then it says, assertion violated. GPA is less than something or other. Or you get to a certain point where you can't register for any more classes, let's say, for example, because you already met some maximum amount. So you try to register for a class, and the class won't go through correctly. Instead, the assertion fires upon the update of that registration record, and it triggers the assertion, and the assertion comes back and says, you know what, you've already exceeded the maximum amount of units that you've used. If you put an assertion, let's say, on a checking account, there's where your auto draft, or your auto, what do they call it? Overdraft protection kicks in on an assertion. So the assertion would actually reject it or accept it, and then trigger a deduction, trigger another row to be entered into the overdraft protection account that on that particular condition say, hey, $5 minus $5, $10, $20, or service fees, or violation of something. Every time you go to an ATM machine, you get $1.50 on an assertion that runs. What location were you at? Oh, not Wells Fargo, or not whatever. Assertion runs. So whenever something happens with the data changes, and it's in multiple tables, you can check for the condition using the assertion on any activity, any update, any removal, anything, you can have it run. So a clever system can observe what is going on at certain changes that would cause a given assertion to be violated. As an example here, no change to beers can affect few bars. Neither can an insertion to drinkers, depending upon what's going on. Did I answer your question or no? Okay. I don't remember what your question was, actually. So that was the last part of this lecture. We are now done with SQL. And it's a good stopping point, actually, for the weekend and for the day. We made it through. So now what we're going to do next time that we're going to meet, and the next time we're going to meet is, I already know this, it's July 27th and 28th. Yeah. We're going to meet at 9 o'clock in the morning on Saturday and run and see how far we get. So I'm going to have a database set up for you guys. I will have a solution. Don't know exactly what the solution is going to be, but we'll have some sort of a database practice solution so that we can go ahead and apply some of this. So we'll create some tables. We'll add some information into the tables. I'll be able to demonstrate it. You'll be able to hopefully log in and do something with it so that you can follow along with what I'm doing and we can have some hands-on practice for it. So exactly what I'm going to create, don't know exactly. I have some ideas I'm toying around with. Probably going to hopefully put a server together. I just thought of at lunchtime, I thought about port issues with the server. So catch me in a month from now. You'll know. So you don't have to do anything. You don't have to install anything. I'm trying to prevent you having to put anything on your computer. So you don't have to install anything on your computers. But the next time you show up for class in July, we'll be doing some more hands-on exercises and stuff. So it'll be less lecture stuff, more activity-based. So I'll be working on some activities for you.
On your system?
I hope so, yes. So
You will have all the tables with the entries.
well, we'll create some tables. We're going to do some stuff in class. We're going to create some tables, update the tables, create some checks, create primary key, foreign key, try to do some stuff where I'll have exercises for you to do. where you'll be doing some. Bring your computer, but we won't have to. Hopefully, we won't have to install anything on the computer.
So it would be better to read that library process.
Yeah. If you're looking for something to do the first 3 assignments. If you have a problem with the 3rd assignment, go review this one. This one is number 5B. It's going to give you everything everyone did know about SQL. And if you need to, you can go at it slower pace and use this as examples for some of the keywords that you'll have to use in creation for assignment number 3, for those queries. So. Those are good questions. Anybody else have any questions? Then you're done. You're free to roam the planet.
Thanks.
Thank you. See you next time. Have a safe trip home if you're flying home.